remember, we can use the lens to project a real image on a piece of paper. And you have two lenses. You have two lenses. This one has a long focal length. This one has a short focal length, okay? I want you to use one lens and then the other to make a real image on a piece of paper. And this time, focus on where the lens has to be in order to create an image. And think about the size of the image. So take a lens. Lenses were in the room. They were in the seats as you came in. And so there should be a bunch of them around the room. Go ahead and lose your lens. Project an image. Try the big lens. Try the small lens. See the difference that you notice. Totally forgot that. So what's the verdict? Which lens makes the bigger image? The big lens. And it's not the size of the lens, it's the size of the focal length that matters. Because when you had that the smaller lens, which has a shorter focal length, is closer to the paper, and so it's got a smaller value of S prime. Smaller value of S prime means you're going to have a smaller magnification, and so the image is going to appear smaller. Okay? Now, given that, let's look at this question right here. This is a picture of someone using a telephoto lens. And you use a telephoto lens to take a picture of a distant object. This relationship applies. This relationship applies. Magnification is equal to h prime over h. That's just equal to negative s prime over s. If you're taking a picture of something, here's your lens and your camera. Here's an object that you're taking a picture of. That's my distance s. My distance s prime is right here. My image forms on the film. Of course, it's inverted, and so I get that. And if I want to make the image bigger, I have to make the ratio of s prime over s get bigger. That gives me a bigger magnification. Okay? So I need to make the ratio of s prime over s get bigger. And there's two ways to do that. One thing you can do is you can just get closer. And you know this, because like I'm taking a picture of Tate, and I want to make it bigger. You can just get closer. S gets smaller, s prime over s gets bigger. The image gets bigger. And that's a reasonable thing. But suppose you're taking a picture of like a lion, say, and something you don't necessarily just want to like get up close to, right? If that's true, your only other option is to change s prime. Typically, for a camera, we have this. Let's imagine you're taking a picture of a distant object with a telephoto lens. S is really big. 1 over something which is very, very big is approximately equal to what? 0. So we can say, we can ignore this, and for a distant object, 1 over f is equal to 1 over s prime. S prime is just equal to f for a distant object. So if I want to make the image of the distant object appear bigger, I have to increase s prime. And how do I increase s prime? I increase the focal length. And so you lose a long lens, i.e. a lens with a long focal length. And that gives me a big value of s prime. And so you can have a lens this is probably like, I don't know, 200 millimeter lens, sticks further out in front of the camera, okay? If you have a digital camera that has an optical zoom on it, watch this. The lens, typically, not always, you can have complicated things happening inside, but typically when you zoom in, your lens moves further out. And it has to. It has to. It has to get further out from the film. You have to increase that value of s prime. And so you can watch for that. Let's do a camera calculation. The image of a 1.5 meter tall woman is 15 millimeters high on a 35 millimeter film in a camera. In the camera, the lens is 50 millimeters from the film. How far is the woman from the camera? Here's the trick with these problems, is you want to take this language of the world and you want to convert this into like the language of like numbers and equations, and you want to convert this into physics. Looks like this. So I have a 1.5 meter tall woman, and she's some distance from the camera. That's the distance s. And the camera projects an image of her on the film. That's a distance s prime. And I don't know what s prime is, and I don't know what s is, but I am given this. I'm given h prime, the height of the woman, her image on the film. The height of the image on the film, 0.015 meters. That's 1.5 millimeters. I'm sorry, it's 15 millimeters. The height of the woman, 1.5 meters. Okay, given that, that's h. So I'm given h, I'm given h prime, I'm not given s, and I'm not given s prime. We're asked to calculate this. How far is the woman from the camera? What am I trying to find here? S. I'm trying to solve for s. And what I can use is not the 1 over f is equal to 1 over s plus 1 over s prime relationship. I'll use the magnification relationship. Magnification is equal to h prime divided by h. H prime divided by h is equal to 0.015 divided by 1.5. 0.010. That's my magnification. And what is h prime over h also equal to? S prime over s. And it's a negative sign, but remember the negative sign just tells us that it's inverted. So we're not going to worry about that one so much. Equal to s prime over s. Oh wait, and we are told what s prime is. I said you weren't. Sorry, lied to you there. Not the first time. I think I was clear about that, right? Okay. In the camera, the lens is 50 millimeters from the film. What is that? That's s prime. That's s prime. And so I'm given, this is 50 millimeters, 0.05 meters. And then I can just calculate what s is. S is equal to s prime divided by 0.01. So it's equal to 0.05 meters divided by 0.01. And so I get 5.0 meters. The woman is 5 meters from the camera. That seems reasonable. Someone's 15 feet away from you? That seems like a reasonable kind of a thing. That's an example of the kind of camera calculations you can do.